Hi, in this lesson, we're going to take a look at simplifying radicals, also multiplying and rationalizing the denominator. We're going to start with talking about the parts of a radical. So the big black symbol that you see right over here, that little check mark looking symbol, is called the radical. The little number outside of the radical that's in the little check mark is called the index. The number underneath the radical, like the 27, is called the radicand. Based on the number of the index, we say them different ways. So if you have an index of 2, that's called a square root. An index of 3 is called a cube root. An index of 4 is called the fourth root. And similarly with 5, it's the fifth root. And n represents the nth root. Next, we're going to take a look at the product rule and the quotient rule. The product rule means that if I have two numbers being multiplied together underneath the radical, I can separate them as two separate numbers being multiplied underneath their own radical. So for example, if I have square root of 15, I can rewrite that as square root of 5 times square root of 3. And similarly, if I have square root of 5 times square root of 4, I can rewrite that as square root of 20. So you can go either direction. Try 21. You'd get square root of 7 times square root of 3. The main goal for simplifying radicals is to find a perfect square underneath the radicals so that we can simplify. But 15 has factors of 1 and 15, 5, and 3. None of those are perfect squares. And same with 21. 1 and 21, 7 and 3 are not perfect squares, so we can't simplify that anymore. If it says to simplify it in simplest radical form, then my answer would be left at square root of 21 or square root of 15. Now, if I get something like square root of 125, I can break that down to 25, so square root of 25 times the square root of 5. Square root of 25 is a perfect square because 5 times 5 is equal to 25. So I'm trying to figure out what number squared is equal to 25. So we get 5, but then notice that square root of 5, there's not a number I can square to equal 5, so that part stays under the radical. So the answer would be 5, radical 5. The quotient rule is similar to the product rule. It's just that we're going to be dividing. So if I have one big square root symbol, I can separate it so the numerator and the denominator have their own radicals. So this would be square root of 17 divided by square root of 144. However, 144 is a perfect square because 12 squared is equal to 144. So this can get simplified even further to square root of 17 over 12. If we take a look at the next one, we have square root of 63 divided by 9. I can divide 63 and 9 evenly, so I get square root of 7. So if you can divide the numbers in evenly first, go ahead and do that. 225 does not divide into 576 evenly, so that means I have to separate them. So 225 over square root of 576. However, they are both perfect squares. Square root of 225 is 15, and the square root of 576 is 24. And then I can also simplify that even farther. So 3 goes into both, so I would get 5 over 8. And then down here, I have just a little note about adding and subtracting radicals. And it says that you have to make sure that the radicand is the same, so the number underneath the radical. So notice in these, it's radical 3, but the last one, it's radical 2. Because the first two terms have a radical 3 in it, then I add the coefficients, meaning the numbers in front of the radical together. So 2 plus 4 is 6 radical 3s plus a 3 radical 2. I cannot add these together because their square root of 3 and the square root of 2 are not the same. Similar to like if you have x and x, you can add the coefficients together, but I can't add an x and an x squared because their exponents are different. They're not like terms. In this case, they're both square root of 11, so they have coefficients of 1 each. So I have 2 square root of 11. Now we're going to take a look at another way of simplifying radicals using prime factorization or the square root method. So what we do is we split the radicand into perfect squares. So if one of the numbers is a perfect square that you're thinking of, then you can go ahead and simplify from there. Or you can break down your factors into prime numbers, and then you can group pairs of the same numbers together. And then each pair, you would take that value in front of the radical in simplified form. Here's a list of some prime numbers. So prime numbers, again, are numbers that have factors of 1 and itself. So they have to be two unique values. That's why 1 is not a prime number. 2 is the smallest prime number. And then you have 3, 5, 7, 11, 13, 17, 19, 23, and 29. 2 is actually the only even prime number. So now let's go ahead and take a look and see how we can solve these. So if we have square root of 24, and then if we think about the factors that would make up 24, we would get 1 times 24, 2 times 12, 3 times 4, 3 times 8, 4 times 6. Now I'm looking at these numbers and I'm asking if any of those are perfect squares. Luckily, the last pair is. 4 is a perfect square, so I want to use that pair if I think of that one first. So I get square root of 4 times square root of 6. I always write the perfect square first because when we simplify it, when we simplify the perfect square, so square root of 4 is 2, the whole number always gets written in front of the radical. Since 6 is not the perfect square, then I leave it under the radical. Let's go ahead and take a look at the next one, square root of 49. So the easiest method is if you can think of the largest perfect square that can go to 98. So in our case, it would be 2 and 49. So then I would break that down into 49, writing the perfect square first, times 2. And then that simplifies to 7 radical 2, because square root of 49 is 7. And then another pair, let's say you didn't know it was 2 and 49, and you figured out that 7 times 14 is equal to 98, then you could break this down. So here's another method. You can break that down so that you would have 7 times 14. 7 is a perfect square, so then we would repeat that one, but then 14 can break down into 7 times 2. So notice that I have 2 square root of 7s, and that means 7 would come out of the radical, and then I'm left with square root of 2. That one doesn't have a pair, so it stays under the radical. And either way that we do it, we end up with the same answer. Okay? Go ahead and try the next example. So if you thought of the highest perfect square, it'd be 36 times 2. So square root of 36 is 6, and then radical 2. If you didn't think of that, but you thought of 9 and 8, you can still get there. Square root of 9 is 3, but then radical 8 still has some factors, so you have to think about prime factorization. Break the 8 down into 4 and 2. So then we have square root of 4 is equal to 2. So then 3 times 2 is 6 times the radical 2 that's left over. And then you'd still end up with 6 radical 2. And then go ahead and try square root of 48. So I show the two different ways to get 4 radical 3. If you think of the largest perfect square, it'd be 16 and 3, hence 4 radical 3. If you use 6 and 8, you'd have to use prime factorization. So square root of 2 times square root of 3 is square root of 6, and square root of 2 times square root of 4 is square root of 8. So you have a pair of square root of 2's, so then that has the 2 that's in front of the radical. Square root of 3 does not have a pair, so we rewrite that, and square root of 4 is equal to 2. So then I have the 2 on the outside of the radical times the 2 from the square root of 4, and 2 times 2 is equal to 4, and then the radical 3 is still left alone. The last piece we're going to take a look at is rationalizing the denominator. Really what that means is that there's no radical in the denominator. Okay? To rationalize the denominator, we need to create a perfect square in the denominator so that when we take the square root of it, it becomes a whole number. So we multiply both the numerator and the denominator by the radical that's in the denominator. So if we take a look at the first example where we have square root of 10 over 3, we got to break it down. We can't have one big radical over a fraction. So this would be square root of 10 over square root of 3. And then we multiply by square root of 3 over square root of 3. And then square root of 10 times square root of 3 is square root of 30. And then square root of 3 times square root of 3 is square root of 9. And square root of 9 is 3. So notice that when you multiply the radical by the same value under the radical, it's always equal to the original number. without the radical. So like square root of 4 times square root of 4 is equal to square root of 16, and square root of 16 is equal to 4. So now let's take a look at the next example. We have 1 over square root of 2. So we can't have a radical in the denominator, so I have to multiply by radical 2 over radical 2. So we get radical 2 over, well, square root of 2 times square root of 2 is 4, and square root of 4 is equal to just 2. And it's okay to have a radical in the numerator. That's fine, just not the denominator. Okay. In this next example, we have square root of 3 in the denominator, so we have to multiply by square root of 3 over square root of 3. And you are allowed to multiply your radicals together. So we get 6 times square root of 6 over, well, that's equal to 3. And then we have to simplify the 6 and the 3. So 3 goes into 6 twice, and 3 goes into 3 one time. So it'd be 2 radical 6. And we don't have to write the denominator because it's just 1. Go ahead and try the last one. So in the last example, we break it down as square root of 25 over square root of 7. And then square root of 25 equals 5. And then we have to multiply radical 7 over radical 7. So you get 5 radical 7 over 7.